better to introduce a virtual memory foundation for scalable deterministic parallelism. First, let me introduce myself. I'm working in University of Science and Technology of China. At the end of last October, I went to Yale University as a one-year visiting scholar. So this work is collaborated with Professor Bramford in Yale University. As we know, with the hardware industry being shifting to multiple and mathematical processors, pervasive parallelism making programming harder, because parallelism introduces non-determinism and data races. All these invite hasselblads, which are sporadic and difficult to reproduce. Here are some examples shows that data races and non-determinism are everywhere. So for memory access and file access, if two processes access the same shared variable or shared files, data race may occur. However, although we can use synchronization to avoid conflict, but there are still several possible results inferring non-determinism. Some system APIs such as malloc and open generate values depending on timings. How can we solve these problems? One promised way is to provide a deterministic execution or programming environment. Current deterministic execution methods such as DNP should promise but allow misbehaved software to defeat repeatability, facing scalability challenges. New restricted programming languages such as deterministic parallel Java and C offer limited determinism, but require programmers to rewrite lexicon and perhaps adopt unfamiliar concepts. Determinator, published in OSDI 2010, is an experimental new deterministic microkernel operating system, offering risk-free kernel programming and compatible with actually existing languages. It provides a check-out, check-in model for shared state and following workspace consistency. So on fork, parent can call system calls put to copy shared state and other states to a child. So each thread of process reads and writes private working copy only. On join, a child can check in its working state, and the parent can get and merge changes accompanied with conflict detection by invoking system call get. So the original determinator has a microkernel, but as an early prototype, there are many limitations. One of the most limitation is its restricted space hierarchy. This figure shows an example of synchronization and communication supported by original determinator. From this graph, we can see P0 forks two processes, and P2 forks another process, P3. In original determinator, P2 has to wait until P3 ends because the original determinator can only support in the inter-process communication between parent and child. Here is another example shows the scalability limiting. In this example, P1 and P2 cannot directly communicate with each other. They have to communicate by way of their common ancestor, such as the P0. In this paper, we propose the SPMC model to increase the scalability of original determinator. The SPMC means a simple producer and a multiple consumer. The goal of this model is to allow arbitrary inter-process communication while preserving deterministic parallel execution. The core part of the model is SPMC virtual memory region primitive at kernel level. We also keep the kernel simple. This is our design purpose. We intend to serve SPMC regions as a deterministic foundation for multiple programming models, as well as I/O as well as scalable deterministic I/O capabilities. For the present, however, we focus on using this SPMC region to support deterministic message passing programming models. To support SPMC virtual memory region, we added two option arguments to the original system calls, that is on and fix. So each process can call get with on to create an SPMC virtual memory, and can call code with copy and on to transfer the ownership to a child process. The process can also call code with copy to hand out the consumer mappings to a child. The producer can call get with fix option to fix an SPMC virtual memory. And also the process can embed an SPMC virtual memory when P does not need it. This graph shows the how the virtual memory maps. So we can see the kernel maps the SPMC regions of the producer and all consumers to the same physical memory pages. Atop the SPMC virtual memory regions, we develop deterministic message passing user space parallel libraries. This library supports multi-threaded parallel programming. It can share read-only state and provide point-to-point communication by SPMC channels and provide a set of collective communication functions. Next, I will give an example to show how does SPMC channel works. So here, first the thread T0 initialize an SPMC. So that means to